So let's get started. So last time, we start talking about bosonic string, but I made some mistake and also some new student here, so I will just briefly recap. So we consider a two-dimensional model, so some Riemann surface or worldsheet, which the trajectory of the string can be understood string to the R1, D minus 1 Minkowski space. So D-dimensional. In D-dimensional. And consider the x mu a coordinate of the target. So this is the Riemann surface and worldsheet, and HAB a metric of the worldsheet, and this x mu, where mu runs for 1 to D, are the coordinate of the target. And then so AB are the coordinate of worldsheet, mu nu are the coordinate of the target. Okay. So we consider this action, and it has the three symmetry: worldsheet diffeomorphism, Y symmetry, and the D-dimensional Poincare invariance. So that's what we have learned last time, and then briefly, so this one is just a coordinate transformation or just worldsheet diffeom, and the Y symmetry is just a scaling over metric, and then D-dimensional Poincare invariance is just a lambda mu nu x nu plus some constant. So that's a symmetry of this action. And then, so since there is lots of symmetries, so we need to fix a gauge. Classically, we take the Lighthouse gauge. Such that the x plus, we impose x plus minus is, this is Lighthouse coordinate of target. Such that we just put constraint is, I forgot the constant actually indeed in the action. So in the action, you have 1 over 4 pi alpha prime, and alpha prime is the only coupling constant for string theory, and then so this alpha prime appear in front of moment. So this is the Lighthouse gauge, and then we quantize the theory. So when we quantize this, and also the one I missed is that the so you can treat this HAB as a dynamic variable. So metric on the worldsheet can be understood as a how to say, you can vary the metric so that if you take the variation with respect to metric HAB and then up to some constant, I already forgot, so minus 4 pi. So this is equation motion in terms of, this will give you equation motion of in terms of metric. And this TAB, if you treat the metric on the worldsheet as dynamic variable, this is 0. Okay? So therefore, what we have learned is that the T minus minus x squared is equal to 0. So indeed, this is equal to, as we learned last time, pressure A, pressure B, x minus GAB, 1/2 pressure x, pressure x. and up to some constant I already forgot, minus 1 over alpha prime. So equation motion is, so this is equation motion with respect to metric. Okay. So this is equation motion of, in terms of for HAV. This is, I missed the last time. So then we quantize the theory. To quantize, we just do the canonical quantization. As we have, I think you guys, okay, most of you guys didn't do the homework. Okay, but, so what we need to do is just introduce the conjugate, how to say, momentum to x, which is delta s, delta partial t, x mu, then 1/2 2 pi alpha prime, and then we impose the computation relation. Sigma prime tau, and then I delta sigma minus sigma prime delta mu. So this is standard. The other computation relation. This will lead you to usual harmonic oscillator for mode expansion in the bosonic mode. So this is usual harmonic oscillator. And then we just act to create a Hilbert space. We create the we act all the how to say negative mode or negative number, bunch of negative number alpha minus nk and alpha theta minus n1 alpha theta minus nk acts on vacuum. That's how you span. So the create a Fock space of the Hilbert space. Yeah. So then, so the consequence of this equation motion. So consequence of this equation motion for quantization will give you consequence is that we just impose for physical state need to obey this. So we create now Hilbert space, and which one is Hilbert physical Hilbert space? So this is a constraints coming from this equation motion. So in other words, this t minus minus t plus plus mode expansion for t minus minus is sum of Lm z minus m minus 2, and I didn't use. Okay, I shouldn't use z minus I and sigma minus. So this is equal to 0. If you sandwich physical state, t minus minus physical state, you should get 0. That it leads to this condition, and also this light cone gauge. This light cone gauge. So this is light cone gauge. Consequence of this one is will give you the constraints that the alpha n plus is equal to 0 for n is not 0. Then we obtain the spectrum of the string theory, so that the equation motion. So equation motion for this string will give you, so this equation motion plus this part. So equation motion partial plus x square equal to 0 would lead you to m square, the mass of the bosonic string spectrum, plus p minus sum of pi, and then which is equal to 4 over alpha prime, and then bunch of mod for bosonic prescaler. Okay, so b minus 2 divided by 2 sum of m. Okay, so that's what we have learned last time, and we just use some regularization of this term, and obtain here is turned into the regularization. Here we get the d minus 2, 24 minus by using regularization, and we define as this numbering operator. This is numbering operator for how many this creation operator acts on the backend that counts this n counts. Okay, so that's what we have learned. And if you consider left moving or right moving mode, what we get is n is equal to n scalar. So this is level matching condition. So that's what we have learned. So the one I missed last time is really this one. So this is the equation motion for the metric. And from here, one can obtain the spectrum of the m square. So mass of the Hilbert space state in Hilbert space. So let's move on. And oh yeah, and also so massless state, in target, so m square is equal to 0, appear as the little group invariant, so SO d minus 2. This is little group inside a SO Poincare invariance 1 comma d minus 1. Okay, so this is a little group. So if you have the massless state, so if you only have it's a schematic, so it's moving speed of light. So therefore, you cannot go to the rest frame. So therefore, the only invariance is also one direction. So this is the SO d minus 2. It's called little group. You just forget about the coordinate of time and the direction the massless state, massless particle or massless string propagate. So in order for the massless state invariant under SOD minus 2, so what we need to do is the D has to be set to 26 here. Then first exercise state, so the essence, first excited state are massless. And it's under invariant under SO. Okay, so that's what we have learned, and we are going to move on to the Conformal V3. So I already raised the string sigma model action is the two-dimensional action, and it's invariant under worksheet. In particular, it's invariant under conformal transformation. in particular, so therefore, so the first part of this course is just learn Conformal V3 to the Conformal V3 in perspective, from the viewpoint of string. So that's what we're going to learn. But first, we need to build up some basic of 2D CFD. Okay, so that's, and the 2D CFD itself is very, very rich subject. I have taught like 2 years ago, or 2 or 3 years ago for 1 semester. So we cannot cover everything. So, but we just build up basic and then move on to the string theoretic perspective of the 2D CFD. So what is a Conformal V3? So let's talk about the 2D Conformal V3. So the conformal transformation in 2D or general dimension, it's a diffeomorphism that is diffeomorphism such that its pullback of a metric, as you have learned in GR, if you do the coordinate transformation, the metric will change. But the particular they change under the conformal transformation, it just the metric is changed under upper factor. So this is the conformal transformation. So in other words, so if you have diffeomorphism, some Riemann surface, and the map to the same topology. So this is a map. X goes to X tilde. But you can pull back the metric here, or usually people just write down I just write down HAV for Riemann surface. But now I'm talking about the general dimension. You pull back the metric to here, it's just scaling. It's just only the metric change only up to scaling. So many students get confused about the difference between conformal symmetry, and the wild symmetry. So the wild symmetry is you don't change anything in the Riemann surface. But as a Riemann manifold, you just scale HAV to you just change the metric. Here, wild symmetry, wild transformation is that you change the metric. So therefore, if you compute the Ricci, or whatever, Riemannian tensor curvature will modify. Curvature would modify. However, conformal transformation is just diffeomorphism. So map from one to the other. And if you pull back the metric here, so this is GAB, and it's a pullback, so the GAB, whatever, maybe I call it tilde. And as you learn in the so GAB, or should I use HAB? Anyway, so GAB is a partial signal. I shouldn't use X. So this is how you pull back the metric. And this one is only proportional to some function. So that's what identity matrix. This is identity matrix. Let's see, delta CA, delta DB, and some factor. That's the conformal transformation. So if you compute, so if this point is mapped to this point, okay? Map to this point, if you compute metric, curvature here, curvature each point, the curvature does not change. So it's just pullback. So the curvature doesn't change. However, wild symmetry will modify curvature. So that's the difference between Gaussian transformation and the conformal transformation. So you have to distinguish. Okay, so then let me move on to so I mean you can consider general Conformal V3 in general dimension, but in this lecture we just focus on 2D dimension. So we will go to the Euclidean Minkowski signature to Euclidean signature, and then in complex coordinate, so Z is e to the what's the notation of my notation? How do I define? How do I define? Well, I have written how the complex coordinate is defined somewhere in the, oh yeah, here. So yeah, so the e to the Z is I sigma minus, and do the weak rotation, sorry. And do the weak rotation sigma minus or minus, so the I tau minus I sigma, and we do the weak rotation, and then what you get is e to the t minus I sigma. I think it should contain minus sign here. So tau goes to it. So this is a holomorphic coordinate, and the z bar is just its conjugate. Then the metric block metric can be written as dz bar. And then the transformation is holomorphic. So if you have holomorphic transformation, the complex plane to complex plane, and the map is some holomorphic function. Holomorphic function means it doesn't involve z bar. So it doesn't involve z bar. Then the metrics, as you have learned in GR, it's easy to compute z partial f bar, f z bar, and dz bar. So this is a scaling factor. So this corresponds to this part. Corresponds to this part. Okay. So this is called conformal factor. This is called conformal factor. And then so the reason why 2D CFT is very rich is that this conformal symmetry is very, very powerful. So as you know, if you do the Laurent series expansion, so this is essentially, I mean, if you do the simple Taylor expansion, for instance, it just becomes f0 plus z f prime 0 and so on, right? If you do the Taylor expansion. And there are infinite many modes one can consider. Z square f double prime on 0 half, and I already forgot how to do the Taylor expansion, so but anyway, so there are infinite many modes one can consider. So the conformal symmetry is infinite dimensional, as we will learn soon. Okay, so then, so the reason why the 2D conformal symmetry is very powerful is that you just have any holomorphic function. So it's an infinite many holomorphic function one can consider. So theory is invariant under infinite many transformations. Outside it's powerful. So for instance, so in the lecture note figure 4 gives you the some schematic figure for conformal transformation. So roughly speaking, so as you have learned in complex analysis, the conformal transformation or holomorphic function just preserves the angle. So the roughly speaking, conformal transformation preserve the angle. For instance, the usual grid becomes something like this way. This is also conformal transformation and so on. So you can take a look at the figure 4 in the lecture to get the feeling of conformal transformation. Okay. Yes. Tau and sigma. Sigma. Maybe I call it sigma. So what I did is essentially I did this kind of conformal transformation. You have a cylinder, and then this direction is theta, and this direction tau. Or to the map to the C star. To the C star means C star is C mod origin. That's a conformal transformation. So here is a radial direction. This is essentially tau direction, and this is theta direction. So radial direction is essentially tau and theta. Yeah. So any questions so far? Any other questions?
That is for
yeah. You should do the homework. Homework 3 to open 3. That's why. So we cannot cover everything. So open string is put it into the homework. Okay. I mean, it's a good exercise. You should do it. Okay. And the state operator. So the So as the John asked, so the cylinder is you can do the conformal transformation to the C star. So therefore, so this is conformal transformation in such a way that, for instance, if you look at the coordinate, it's just plus. So you have dx squared plus dy squared. So in radial coordinate, it can be written as like this way. This is r direction. This is r, and this is theta direction. And this can be understood as r cross d log r squared plus d theta squared. Now, whereas on the other hand, in cylinder you have ds. This is also you can understand the strip identified two edges. Okay, two edges are identified. So therefore, you can have a flat metric, and the flat metric. So this is tau direction, and this is I call it sigma direction. Sorry, so I think I call it sigma. So I should use sigma. Sigma. Yep. So I hope I have written lecture note in the week notation somewhere, but I already forgot where it is. And please read the updated lecture note. There are lots of typo. I continuously change the lecture note, so and the update in the e-learning. So please take a look at. Always update your lecture note. So, yeah. And this is dt squared plus d sigma squared. And as you can see, t, if you can identify t is log r, and sigma is theta. You can just do that this transformation, and then you can bring it to the this metric to here up to some factor. Up to some factor. Therefore, this is conformal transformation. And then, so the most important, one of the most important thing in Conformal V3, you have state operator correspondence. I briefly mentioned at the end of the lecture. So the state on a cylinder can be understood in Hamilton homoformalism. So states are propagated on the time direction. Okay. And as you do the conformal transformation, so state, this circle is mapped to this circle here. So the scaling on the radial direction is also the conformal transformation. You can just have any scaling on the radial direction, so that as we go back to the origin, as we approach the origin, this state localized to the point here. Okay. Therefore, if state shrinks to the point, it becomes operator. The operator O and the state O. In Conformal V3, there's a one-to-one correspondence. Because one can do the conformal transformation to shrink this state into the circuit into the point. If it is not conformal, so this is not the case. There is no state operator correspondence. I mean, non-conformal V3. That's one of the reasons why it's hard to deal with non-conformal V3. The quantum V3 which is not conformal. Okay, so that's the state operator correspondence. Yep. So now, the dealing with states, the same as dealing with operator in Conformal V3, and we would like to understand how the operator behaves in the Conformal V3. That's what we are going to learn in free boson. In free boson. So now, so we just set the HAB as let's see, HZZ bar to be flat, which means 1/2, and the HZ bar Z is 1/2, and otherwise 0. And the action becomes as follows: 1/2 pi alpha. The string sigma model action is just a free scalar field in the free scalar field, and a bunch of mu rounds for 1 to d. So this can be understood as just a d copy of free scalar. Okay? D copy of free scalar. So it's when you learn quantum field theory in Pascal, so you start with free scalar and then quantize, right? So we will do the same thing, but now it's conform. It has conformal invariance. So in 2D, so we have some rich structure. Okay, so I already did model expansion. So the equation motion is partial bar is x is equal to 0. So this is model expansion. Therefore, the free scalar is holomorphically factorized. C plus x bar, C bar, and this is left moving and right moving. Which one I call right moving? This is right moving and left moving. Okay, so if the free scalar is holomorphically factorized, then it's automatically a solution, right? So it's easy to see. And then you just do the free transformation. I mean, I just write down, that's what we have done, but we're just working on Minkowski. Instead of Minkowski, Euclidean signature, and moreover complex coordinate. Log C I alpha prime over 2 sum of alpha b n c n. So this is is a mode expansion. You just do the free expansion. Oh, and then left moving, you just do the complex conjugate. For Z. Okay. And now, so we'll introduce something very, very important notion. So introduce some important notion into the CFT called the operator product expansion. So operator product expansion, operator product expansion, and people just usually use OPE into the CFT. So this is very, very let's see. So the notion is essentially if you have an operator at point Z and another operator or let's see, O prime W, and then so notion of OPE is just when this operator approached to the one operator approached to the other operator, you can approx the product. You can have product of in terms of operator such that the some coefficient which depends on Z minus W as far as remember, and you have another operator. Let's go instead of prime. Let's go I, J, and K, and then K, I, J. So into the CFT, so this how the operator behave when one approach to the other is very important. So it gives a lot of information about the Conformal V3. And then we will use the Prescaler as an example to understand how this operator product OPE works. So for instance, to get the OPE, so we consider path integral, and then insert okay. So let's consider the so here so as we do the Euclidean path integral in Euclidean signature and take variation with respect to Prescaler, and then we just get the equation motion that is d x e to the minus s and 1 over pi alpha prime partial x, and then 1 pi alpha prime, and this can be understood as some expectation value of the some operator. So this is the some path integral version of the equation motion. Okay, and then so we insert some operator in path integral and do the same thing, and then you will see something a bit more interesting. So now we insert. Okay, let's use this one. Any question? Yeah. If you have a question, please tell me. Just ask. So you just insert some operator here now. X new W bar, and then what we going to have is in addition to, let's think about X mu. In addition to this piece, which depends on, we now assume Z bar and X nu W bar. In addition to this one, so this now, so variation with respect to X acts on S action, and you get this term. But now this one can act on this this operator, and you have an additional piece which is A mu nu delta function, which is delta function. So here it will change to something like x z bar and x ww bar, and it's just C number, A mu nu. The other function is just C number. So that's what you get. So this is the path integral version of equation motion. It's a very simple thing to do. Then, so once into the CFT, we can do the following trick. So if you do the Stokes theorem, so as you know, that in complex version Stokes theorem so this is equal to 1 over I partial d b dc minus b bar dc bar. Okay. So therefore, so one can take if you do the Stokes theorem. So once you apply partial bar log z, okay, square, this is equal to 2 pi delta square. Do you know how to apply this Stokes? This is familiar Stokes theorem, and this is the, if you use this Stokes theorem, one can derive this one. How do you know how to do that? Can anybody derive this? So you just apply. Okay, you just apply this integral in both sides. You just apply integral on both sides, dz square. And here you just do the same thing. I think I need to include 2 pi is here. Anyway, so if you apply the same thing, okay. Then here, left hand side is just Stokes theorem. So you get the okay. Let's use 2 pi. Like 2 pi. Oh my goodness, it's too complicated. So 2 pi cancel. So you get the d squared z. Okay. Okay. So if you apply the Stokes theorem, what you will get is 2 pi I, usual complex analysis, dc, here partial bar log c square plus dz bar, minus dz bar 2 pi I partial log c square. This is left hand side applying the Stokes theorem. Do you agree? Is it okay? I just apply this one into the Stokes theorem. Just apply this one and look at that, and maybe 1/2. Well, do you need to include 1/2? I'm not good at the coefficient, to be honest. So this b bar can be so this quantity can be answered b bar. Okay. And another thing, this one can be understood this axiom. That's what I did. I think I need 1/2. I guess I need 1/2. Yeah. And now, if you do the if you apply delta z, okay. What would you get? So this is just a log z plus log z bar, right? This is log z bar. And the only anti-homomorphic part matters. So you get the, if you act on 1 over z bar. Okay. And also here, if you do the same thing, you get the 1 over z. And one can do the contour integral. You get this is equal to 1. And here, you get the 1. Because it's just delta function of 2D. That's how you derive. Okay. Is it okay for you? So therefore, in 2D, if you use the Stokes theorem, one can replace delta function here is partial bar log z squared. Is it okay for you? Okay. Yeah.
Your integral is, for example, like integrate the z bar along with the bar with z.
Oh, measure is something wrong. Then it should be type or something. It should be consistent. It should be consistent. Z bar and z. Sorry. Yeah.
You can replace z by some e to the I z, then integrate over z.
Does it give you the right answer? So what we want is this one, 2 pi I, z is equal to 1. If it is z bar, does it get minus 1? If it is z bar, what would you get? Do you remember? Let's see, z, let's do that now. So z is equal to e to the 2 pi I, r 2 pi I squared, and dz is equal to, essentially contour into d squared, 2 pi I, squared, but you can have z bar integral, right? Does it? Nothing wrong with it. You get the minus sign. I think sign is wrong in that case. Okay, I will fix this one notation later. But you understand what I mean here. Sign or bar is wrong, whichever. You understand what I meant. Let me think. I think I don't know. I need to. I'll fix it during the mid break. Okay. So now, we can use this is equal to delta 2c. So we can use delta function can be replaced by this two derivative act on the log of z squared. So therefore, getting rid of this expectation value. So what you get is mu z bar. So this is one example of the operator product expansion. Log c minus w squared plus so now we replace delta function in this quantity, and since we both have two derivatives with respect to holomorphic and anti-holomorphic, just forget about it. Then you get this equation. Since this is normal order product, so therefore all the creation operator goes to the left and annihilation operator right. So therefore, if you take expectation value, you get 0. Okay, do you understand? So therefore, this is normal order product. Normal ordering. So therefore, if you take the expectation value, you get 0. And then, so this is the one example OPE. So this operator Z at point is approaching W, you get something singular behavior here. That's what this one example OPE we derived. So I will fix this part. Some sign or holomorphicity is wrong in this convention. So I will fix the problem into the mid-grade. Okay. So. Any questions so far? Is it okay? Yep. No, I just get rid of average. No. I mean, you can put average, then this term vanishes, and you get this equation without derivative. So here you have the two derivative. Here you have the two derivative. I just forget about it. Any other questions? Okay, so this is the starting point of the OPE of free bosons, free scalar. So then we can do many things. So for instance, we can do many things for. We can understand lots of things about from here. And for instance, so normal order product can obtain, for instance, in principle, one can just act minus 1/2 d squared w g w, and acts on fx. So this is in principle one can obtain the normal order product for any operator which is written x. So you just apply the variation into the function, and you get that g is indeed this one is g z w. I define this is a g z w. And if you so this means okay, let's do exercise. So for instance, let's consider x1, x2, x3, x4. The operator product expansion like this way. Then what you will get is I mean, you can take the many contraction. So x1, x2, x3, x4, and then I mean, you have if you try to study Conformal V3, operator product expansion is very essential. Let's make the problem very simple. It's a bit annoying to consider 4 operator, so let's 3 operator is better. So for instance, I walked into the Conformal V3 like 1 year ago with Zhang Hao. He did lots of calculation of OPE. So in 2D CFD, OPE is very, very important notion. So you have to be fluent. So one can contract. Essentially, this acting on derivative is essentially the contract to operator and replace G. So what we get is G. So this one is equal to G12 x3 plus x1 G23 plus x2 G13. That's the operator you will get. Of course, I just considered x1, xi as x of the I. And I forget about the anti-homomorphic part. and Gij is the this guy, G, Zi, and Vgj. So that's OPE you get, and so on. So if you increase the number of the operator, you have to take a bunch of combination of the this contraction. So yeah, I mean this is a definition, but if you try to do the OP calculation, I mean contraction like this way is the practical way to do the OP calculation. Yeah. Okay, so let me move on. And also, let's see. And of course, here I just sorry, I think I should write down. This is the only idea looking at the singular part of the singular part of OPE. So essentially this is equal, if you want, so this normal order product is actually normal ordering here is ignored here, sorry. So it's this, how to say, in LaTeX it's sim, right? Sim is essentially you only look at the singular part of the OPE. Singular part is really here. So when Z approaches the W, some singular thing occur here. That's what I meant by singular part. Okay. So singular part is most important. I will tell you why it's important, because you can do the contour integral. And also, one can take the multiplication normal ordering f of x. There are two normal ordering for some function with respect to x, and then we can just apply the same thing. But now we have, I mean, it's just the same thing. But anyway, so this definition doesn't tell you something interesting. In practice, you have to do contraction. I will tell you. So, but I just give you the definition how to do it. So the bar acts on F, and then dx mu acts on G. And then unfortunately I don't have a space, so this acts on the product of normal ordering. So this is definition, but this is not practical. So I will tell you how to do the practical thing. So for instance, I can, where's the choke? Oh yeah. So for instance, as an example, if you take the product of two operator, for instance, I'm going to omit the anti-homomorphic part because it's the same. Okay. Essentially, so this operation is essentially get rid of 2x and replace g. Okay, that's so get rid of 2x and replace GZW. Okay, GZW, and then the rest part is just a normal order product. And of course, if you apply the z derivative, what you get is the minus alpha prime over 2 eta mu nu. So let's forget about eta mu. theta mu nu, and then take derivative with respect to holomorphic coordinate, which means z minus w divided by 1. Okay. Okay. And then, so this is, I call it sim. So I forget about the normal ordering part. Only look at singular part. So this is the how you do that. And also, so this is very important thing we consider that. So this is called Vertex Operator, which plays very important role in string theory. So this is the, you can have any function of the operator, e to the some power of k. So this is a very important operator in string theory, and you can take the product of this one. And then, of course, you can use this definition, but what you practice, if you get confused, you have to go back to the original definition in the calculation. But practically, one can do the following thing, so that you can have this is equal to exponential of ik times ik prime times minus alpha prime over 2 log z minus w squared. And then, unfortunately, I don't have a place to write the rest of the part, so I'm going down and the e to the ik xz plus ik prime x w, and then normal ordering. Okay. So, yep. So here, you just, what we have done is just replace x mu from each side and take exponent, and replace g and take the exponent. Okay, and then one can compute this exponential, since the exponential log cancel, and what you would get is something like z minus w and alpha prime k dot k prime. So that's what you obtain for OPE of 2 vertex operators. So these are called 2 vertex operators. So this will tell you how it behaves, this vertex operator approach to each other. And you have to do lots of calculation for OPE when you study 2D theory. Okay. Any question? So, yep. So let me a bit more proceed. So you have to be careful about here. So you have to be careful here. So sometimes you have some, I mean, this is not the example, but see here you have an operator depends on Z, and here operator depends on W. Therefore, to really see that how the XZ, the operator here approach to XW, you have to do the tail expansion for this part, tail expansion for this part, and then precisely speaking, what you will get is so this one is equal to x mu ww bar. So now even x depends is how to say this operator that only depends on w, but we need to do the tail expansion so that the rest of the part you just need to act the derivative on here. Plus, so this is equal to plus sum of k factorial z minus w to the k, and then can I just write down holomorphic part? Mu and x nu and ww. And then anti-holomorphic part. So you have another thing, dz bar, and then anti-holomorphic part. Plus. So you just take conjugate, and then bar. That's what you do. You have to do it. Now I just did the tailor expansion of this operator. Okay. So that's how you obtain the OPE. And then we will gradually understand what the power of the OPE or importance of OPE from now. To see that, let's see which one. Let me. Okay, I will erase. I will correct everything in mid-break about notation. Okay, so now in quantum field theory, given a quantum field theory, the basic question one can ask is that any quantum field theory you have any physical theory, you always have the stress energy tensor. And then in quantum field theory, this can be this can be understood the operator, some operator. Because now in free scalars, it's up to, I already forgot that. Is it the case? Anyway, so sorry. So I think in the if you consider only holomorphic part, essentially up to some constant, you have this operator. Up to some constant partial, the holomorphic derivative. So this is the operator. This, as I mentioned, so any function of f, and also you can apply the derivative on x. So this can be understood operator. So any physical theory, you have a stress energy tensor. And in quantum theory, stress energy can be understood the operator. And the question is, what is the OPE of this one? So this is a very fundamental question one can ask in physics. So we are moving on to answer the very basic question in quantum theory. Okay. In particular, this product is very important in to the conformal theory. That's what we are going to learn, which is related to this is very related to infinite dimensional conformal theory, infinite dimensional conformal symmetry, and also symmetry. And to understand symmetry, as you know, so the Tensor theorem is very important, and also in quantum version of Tensor theorem is what Takahashi Identity, and which we are going to learn. So, yeah. So Tensor theorem tells us that the Tensor theorem tells us that if there is symmetry, if there exists symmetry, then you have a current, associated current. There is concept current GA associated symmetry. That's Tensor theorem. And also, if you do the integral into this two-dimension, so in two-dimension, this is the conserved quantity charge. So this conserved current and the conserved charge. Okay? This charge is conserved. So this is a Prescaler theorem, and in particular, if there is symmetry, you have the action of delta S is equal to 0. So this symmetry means that delta S is equal to 0 action at the classical. In quantum mechanically, you have to be careful. Sometimes, if there is symmetry, there is some anomaly at the quantum level. So you have to be careful. But if the measure of the path integral is invariant under the symmetry, its symmetry is preserved at the quantum level. Otherwise, it's anomalous. And then, for instance, in quantum theory, you just learn the measure is not invariant when you consider this. You just consider the triangle anomaly or chiral anomaly in what you learn in quantum theory 2 or something. That I taught last semester. No, 1 year ago. So you have to be careful at the quantum mechanical. So we will learn something about the anomaly in 2D. Maybe next lecture or after 2 lectures. But now we consider a quantum version of the this Tensor theorem, which is called the Takahashi Identity. So instead of now, so here usually you have e to the some take the some function e to the some function. E can be understood a constant infinitesimal transformation for symmetry. But now we just upgrade the E has a dependence of the coordinate. Then this path integral approach or the variation with respect to the variation and action with respect to this will give you the following. So now it's the variation no longer 0. So if it is not constant, so what you get is instead of taking usual variation, you just let's consider hat. So if epsilon is dependent coordinate, then the hat S is equal to something like that. If you take the variation with respect to, it's no longer 0 and it depends on some coordinate. And then you have current. So it's no longer 0. And here you have so you have DC. If you write down the holomorphic coordinate, you have 2 pi. And the epsilon z bar. And then holomorphic coordinate, it just becomes like this. Okay. So if parameter is constant, if you take integral by parts, you can easily see this is 0. But this is not the case for when epsilon is no longer depends on holomorphic coordinate. And now we consider a bit more this version in path integral. So let's consider the following. If you insert some operator in path integral, e to the minus s, and then consider some operator and take variation with respect to the delta hat, then what you will get is something like this one, dx e to the minus s, and the operator O, W bar, minus delta hat S of O, W bar. So this is very simple operation one can take in path integral. This is called Takahashi Identity. Okay, so Now here I take the here I take epsilon z is the following thing. So the given complex coordinate c and point w, I have an operator. And now epsilon, I just take the certain unit circle, So epsilon z bar is constant on this disk, otherwise 0. So this is the disk containing. So this is dw. Disk containing around the point w. So if you take this the word Takahashi identity, one can show that in operator formalism, so one can consider. So we now know that this delta S will give you this quantity. So that the what we can show is that we have delta operator with respect to this symmetry in quantum level can be understood as this one. And the operator And if you do the contour integral, so as you can see, I just substitute this one into here, and I forget everything about this. Now it assumes there's some, it's inside a path integral. It's inside a path integral, so I omit the average. So it's you can understand as that's what we have done for OPE, right? So we omit average, the expectation value, and this can be understood the equation as an operator. So now here we need to do lots of things about OPE and so on, J and O. That's what we are going to do. And so here, if you take epsilon as this value, so what you can obtain is epsilon over 2 pi I, and the boundary of dw and dc j of c minus dc bar j bar of dc bar operator. So this can be understood the word Takahashi identity. So this is word Takahashi identity. So this is essentially here everything. I omit this path integral part. So I will omit all this path integral part. Okay. So this can be understood inside a path integral. Word Takahashi identity. Let's take a break, and then I will give you a meaning of this word Takahashi identity after the later part of this lecture. So I will give you some example and the implication of this word Takahashi identity in the second half of the lecture. So let's take a break. So if you have questions, just tell me. Oh, yeah, and I have some souvenir for you. This is called Tonosha. So you can have one. You can have one. You can open and you can have one. I think it's. Yeah, you can have one. Just you can just open and take the one. So if you have done the homework, just submit now. Yes.
So this one is possibly G3+1.
It's very simple. So G is GAB, partial MJB, right? And now GAB is only like a GAB. I mean, DS squared is D squared.
Oh, I see. So there's only one diagonal.
I want to ask, I still don't understand why this term is equal to this, since this seems different from this one.
Yeah, you use this one.
Just use this formula.
Yeah. So you have to use this formula. And then, so this acts on F. So this acts on F, this acts on G, and just replace G.
Why this is only the partial for C?
Because here you have partial for C. So I think I should write that C.
Yeah.
Yes.
That paper.
I forgot to bring.
Oh.
So after lecture, let's go to office
Okay.
and then give it to you. Okay, thank you. Yeah.
Question on this situation.
Okay.
Because when you prove it, you can actually add an integral.
Yeah.
So I think they just equivalent to each other within the integral. When you add it on the situation, you take off the integral. So do they actually equivalent to each other everywhere in the complex plane?
So D can take any domain. So D can take any domain in the
So I can take a very small.
very small. Yeah, that's why.
Thank you.
Oh yeah. Or I can just. Oh, Tom. Okay. Jack, can you come? What does it say? So what should I write?
Basically, the first is ask whether it's viewable or not,
Okay.
and the second is what's the problem, and you have to give some suggestion.
What's the problem?
What's the problem of this project,
Okay.
and you have to
Okay.
give a suggestion how to fix it.
Okay. So what should I write? This about what is the problem?
What do you mean?
Do you think it's enough?
I think it's okay.
Are you sure?
But this is signature as it's a sign in hand, I think.
Oh, hand.
Yeah.
Oh, okay. So then, I will have iPad. So, do you think this is enough? Let's see.
Perhaps you just say you agree this. You agree my choice as
Okay, I think this is okay.
Yeah.
And then I will. And then I think I can just share AirDrop and come to here. It should come here. Just 1 minute. Why it doesn't come here? Gosh. Oh my goodness. Huh? Why it takes so much time? Is it problem internet?
Did you use the
Here, that's why. I see. Okay, let me do it now. Okay, let's send an email and then I can receive. Oh, do you have some notepad?
No.
Do you have iPad? Oh, okay.
I can write.
You can write. Okay, so which one is your iPad? Can you turn on the AirDrop?
AirDrop. I don't think I have one. Or you send me by WeChat.
Okay. Okay, then I will send you a WeChat.
Yeah.
And then bring it to iPad. I will sign. Is it okay? Wonderful. Okay, I send you.
Okay.
And then can I sign? Yeah.
Okay. Oh, okay. That's black.
Great.
Okay.
And here's, I just need the signature, right?
Yeah. So I will print it
Yeah.
in Kanban. So
And date is,
and I will hand in.
yeah, 22,
Afternoon.
21.
21. It's March. The okay.
March 12.
Oh,
Is it okay?
I think it's okay.
Okay, thank you very much. Okay, so let's resume. Okay, so you can hand in homework now. If you. Oh, did I tell you something about the role? So if you can hand in homework either PDF by attaching PDF to the e-learning, or you can submit now. Bring your homework to here. And what I'm trying to say? Oh yeah. So if the so then so summation after due date is the count 80% of a grade. Summation after solution is sent, it's 30%. That's a rule. Okay, that's a rule. And then yeah. Anyway, so if you really want to understand the string theory, it's better to solve it. But anyway, there are many auditors. It's okay. I mean, if you just want to listen, it's okay. That's anyway. So if you want to get some grade, you need to solve homework. Otherwise, you can just come here and audit. Okay. So you guys had a meeting with Janet? Oh, okay. Okay. Every Friday morning? Okay. Today is just coincidence.
Sorry, we don't have a new question.
Oh, okay, okay. Okay. So let's move on. Oh, what else I tried? I tried to say something. Forgot. Oh yeah. So you can just call me Satoshi. Don't call me like a professor or Laoshi or a teacher. And you can just call me Satoshi. I know in China there's some hierarchy between professor and also students, but you can just call me Satoshi. It's quite amazing. Amazing. Oh, Wang Hao is here. Oh, okay. Yeah. Some of the students here can speak Japanese very fluently, although I cannot speak Chinese. At least 3 students here can speak Japanese fluently, as far as I know. But anyway, so you don't need to use you can be very frank. Anyway, yeah, even I think Japan is more like a severe hierarchy than China. I think. Yeah, and then if you're in China and in Japan, you have to be a bit careful about the honorics and so on. But I don't care. Seriously. Anyway, so let's start looking at the example of Takahashi Identity. So okay, let's look at the example for this Takahashi Identity. Of course, the example is free boson, free scale theory. Now, so as you know, the free scale theory action is something that 2 pi alpha. Is any action written here? No. 2 pi alpha prime. This is action, essentially. And as you can easily see, there's a symmetry. X goes to X. So X depends on coordinate Z and Z bar. Is you can just have constant shift plus some constant shift, some extra, some constant. This is symmetry, as you can easily see. If you take a variation with respect to constant shift, like a delta X is constant, then of course it's derivative X on constant is 0. So you can see it's a very simple symmetry. It's just translation of the space-time. Okay. So this is the most. But now we can upgrade epsilon as a coordinate. Depends on coordinate. Then now delta hat S is again can be written 2 pi alpha. Oh, I didn't. Okay, I need to fix this this issue. This issue. Okay, I will do. Sorry, you should remind me. I need to fix this issue. 2 pi. I need to fix this issue. So, but after that, this one. You should remind me. Yesterday I teach, and the afternoon I prepared this lecture, and now my brain's no longer working. So you should correct me if I'm wrong. So epsilon z bar. And then if you take the variation, just do the integral part, you get this one partial x plus. So do you see that? Do you see this one? If you upgrade this one is a symmetry to the coordinate, do the take delta x as so now delta hat x is just a epsilon z bar. Okay, take this delta hat x and then do the integral parts, you get this term. And if you take delta x and the integral parts, you get this part. Okay, do you agree? Do you agree? So now comparing this one and this one, comparing this one and this one, you can easily confirm that the J is equal to this one up to some constant. I'm not gonna write. J bar is minus alpha prime partial bar x. Yeah. So this is the homomorphic current, anti-homomorphic current for this translation. And then you can apply the okay, x, w, bar. Okay. Okay, so that's what you get. And now you can apply the OPE. So for instance, you can take OPE this one and OPE of this one, right? And now I think I omit some constant. I'm not careful about constant sign. That's why I made a mistake over there. So you have to fill up by yourself. So if you take OPE, OPXX, did I erase already? Yeah, I already erased. So minus 1 2 pi. So if you take OP between them, what you will get is the so minus partial bar, partial acts on the minus alpha prime t log z minus w square. Do you agree with that? So here, if you take OPE of this one, you get this one, and another piece is the same. Essentially, you get the 2 copy of this one, 2 copies. So it just the order of the action is opposite. Okay? And now what you will do is apply this one. Apply this one and 2 times of this one. Apply 2 times this one, you get the delta function. And then 2 pi cancel minus 2 alpha prime d squared z 2 pi epsilon z bar and delta function. Okay. Then you get original equation. So can I erase? Oh, maybe it's better not to erase, or you already take a note. Let me erase. And then apply delta functions, and up to constant, it becomes epsilon w bar. Okay. So if you are careful about the constant, so I think this alpha prime cancel and 2 cancel somehow, and minus sign cancel. I'm not careful about this one. Essentially, what's happening is the integral of epsilon times delta function will give epsilon. Okay, a constant will automatically cancel if you're careful enough. Then we get the original derivation. Delta x is epsilon. Okay, that's what you get. Do you agree? That's the power of OPE. So the singular part is most important because it appear in the contour integral. So you always, in 2D CFT, you always need to do this, lots of this integral to pi I z. Okay, essentially, you apply many things on this one to the singular part, and then you get the answer. So that's why singular part is important in OP. So this is the original variation, right? That's how you get the original variation out of the word Takahashi Identity plus OP. Okay. So let me move on. So now, now we need to fix this issue. And then let me. So there is a typo in the reason why I made a mistake. Yeah. Is that somehow I don't know. I need to look at the recorded video. So I don't know why I made a mistake. It's very simple. I don't know why, man. I think you should. Some of you already noticed. I think what I have written in the blackboard is wrong. I think you should correct me. So the Stokes theorem is in fact. This is the Stokes theorem. It seems like I just swapped B and B bar in the first half of lecture. Seems like I swapped. I think if this is correct, and then let's apply the same thing. Partial log square. So we want to obtain this one, right? And then you just apply the same thing. Yeah. I don't know why I made a mistake. For instance, which one is the correct order for derivative? Okay. Yeah, I think I shouldn't get the right answer. So if you apply dz squared, I don't know why I made a mistake. Let's see, 2 pi partial bar. You should correct me. I think some of you already noticed during the lecture. Dz squared 2 pi delta 2. Okay, I want to show this equation. So left hand side is this. Okay, let's look at left hand side. And then you apply this one, you get the dz 2 pi I, and partial minus. So you need to apply this one and this one, so minus log square. Okay, I think good. Then dz bar, okay? dz bar. So you only look at this part. Then what you will get is essentially dz bar 2 pi I d bar, okay, and minus sign because we have anti-holomorphic part, so you get this is equal to 1. So instead of anti-holomorphic means that instead of the counterclockwise, you have to go clockwise. Therefore, you get the minus sign cancel, and you get the 1. On the other hand, this is equal to just automatic 1 due to the differential delta function. Okay, that's how you get. I think in the first half of lecture I mixed up with bar and without bar. I think you swapped. That's why I made a mistake. Okay. Yeah. this is a consequence of giving lectures 2 days in a row. I already lost my Fudan card yesterday. So let's move on. Okay, so now we are going to look at the, instead of, so using, apply word Takahashi Identity to the conformal word, conformal symmetry. So that's for conformal word, conformal word Takahashi Identity. So now we just consider the infinitesimal, so-called the conformal word Takahashi Identity. So now we know that the conformal symmetry is just a homomorphic function. So therefore, x mu plus e mu of t. So this is the we are going to consider holomorphic transformation. So under the metric under the conformal transformation, it just scale as the conformal factor. So therefore, this is the infinitesimal Correspondence transformation. The metric is the, so this is the infinitesimal version of the G mu nu. I mean, I already explained many times. I mean, if you learn GR, you get this one, sigma rho, and you just apply this one into here, you get this one. Okay, so it's very simple. And if we and in order for, okay, so this is just the infinitesimal Correspondence transformation or diffeomorphism. In order for this one is conformal symmetry, so we need to have the impose Do you know how to obtain this one? Do you know how to obtain this? Do you know? So since we know that in order for this, so this is just diffeomorphism. In order for this diffeomorphism to the conformal symmetry, this one has to be proportional to eta mu nu up to scaling. Okay. Therefore, this part is proportional to eta mu nu, and the question is what is this prefactor? But this prefactor can be fixed by taking trace. If you take a trace, you get the 2 here, the 2 copy of this one in left hand side. Therefore, automatically this factor is fixed by taking trace. Yeah. So then, so this is the conformal symmetry, and now we just look at the current of this conformal symmetry. So this, again, one can apply the same method, and we just can obtain it. This one, T mu nu. This one nu, where the, I mean, this is general, if it is general, theory, T mu nu is just another way to define a flat space. It's just I mean, it's just an infinite theorem method instead of GR method, Lagrangian. This is just a definition of serious energy tensor in field theory. You already learned many times during the past lecture. So this is general conformal field theory we are looking at, not free boson, not only free boson. Okay. So if you assume epsilon is constant, you can just easily obtain the conservation of the conservation of the this necessary current is the same as conservation of stress energy tensor. And then so, and if it is epsilon is constant, it's just this one. And it's so for general epsilon, so if epsilon can be any function, so if epsilon is some function, so this conservation of the, so this is, I assume epsilon is constant. So now if epsilon is some function, this conservation is just a okay, so this is the case, and this means that the T mu in Conformal V3, this one is Conformal V3. This is the consequence, classical consequence of the symmetry, conformal symmetry at the classical law. Okay, and the holomorphic coordinate. So let's, if you write the holomorphic coordinate, and then conservation can be written as this. This is the conservation of the source energy tensor. So therefore, as you can easily see, so TZZ is holomorphic. It only depends on holomorphic dependence. ZZ bar is anti-holomorphic dependence. So this means that the TZZ is holomorphic dependence. TZZ bar is anti-holomorphic dependence. So that's the consequence of the equation, the conservation law. And usually people just write down this one is TC, and this one T bar, T bar. Okay. And then JZ is just a J bar, T bar, epsilon bar, C bar, and T bar. So this is network current of a conformal symmetry. So then Takahashi Identity or conformal, let's see, conformal symmetry, just plug that one into there. Okay. Then plug that one into here. So I'm lazy, so I'm going to use this one. So since I'm a lazy person, just use here, and then just plug this one into here. Then what you will get is essentially here is so the Z, epsilon Z, TZ, and then here you have TZ bar, epsilon bar, C bar, and T bar, C bar. Okay, so this is conformal Takahashi Identity. Any question? Oh, and I need to erase epsilon. Okay. Any questions so far? So now it's getting a bit more interesting. So in the note, I just take this is counterclockwise, and then I just began in the note I made it plus, and it take clockwise in the anti-homomorphic part. So that's a note. But anyway, so here I just consider the counterclockwise, just usual counterintegral. questions so far? So now it's going to be a bit more interesting. So now people will understand that. So we would like to take OPE of this one. Now OPE of source energy tensor on the operator. So that's going to be very important from now, as you can easily imagine. And then what we are going to do is it's quite a So we'll consider the OPE between T and some operator, and then some nice operator behave very. If you pick like a nice operator, it behaves very. Well behaved. It's well behaved under this OPE under the stress energy tensor. That's called primary field. So some nice operator behave very well under the OPE with stress energy tensor. That's called primary field. And to introduce primary field, I will give you a bunch of notation. So now, if phi is a scaling, so there's under scale. I'm going to omit everything of the anti-holomorphic part. So I'm only focused on holomorphic part from now. Holomorphic is scaling. If the scaling transformation will give you prime is lambda minus h phi of t. Then h is called the conformal dimension. And then if this is the conformal transformation, phi of t is mapped to oops, I'm going to omit the homomorphic part. Phi of t. So this is if the in conformal transformation, if field behave like this way, it's called phi. Phi is called primary field. It's called primary field. If the field, the operator or field behave like this way, instead of in the scaling transformation, the field always behave like this way. But this is not necessarily the case for any operator. But if operator behave like this way, it's called primary field. And in conformal theory, so there is some special conformal transformation which called z goes to under so where a b c d. So of course this is a holomorphic function. For example, it's a conformal transformation, but it's some special conformal. I will say some special type of conformal transformation, which is SL2C or SL2C or C2. But Z2 means Z2 is you just identify 1, 1, 0, 0, minus 1, minus 1. So you just identify minus sign. So when ABCD satisfy this matrix, which is inside the element of projective SL2C, and then phi of z, so it's a bit slightly lighter. So if this, that's called G, so let's call this G. G of z, and under this transformation, if field behave like this way, then it's called quasi primary field. So, and then H bar is always called conformal dimension. I mean, in Polchinski it's called weight. Polchinski call it weight, but I think conformal dimension is more frequently used. So I use conformal dimension. Now let's look at this. Why this prime? So to look at the why, the reason why it's interesting to think this primary field is we can just take the OPE with the stress energy tensor. So we can just take so this part, I just take the infinitesimal transformation of this one. Minus h1 plus h threshold c epsilon plus O. So that's how I just take the f of z is just an infinitesimal transformation, like this one. So then, so if you look at this infinitesimal variation for primary field, we are going to take so homomorphic part, this can be understood. So this one and this one are the infinite variation. So that what appear in the infinitesimal variation, and consequently, and then we can just take the we can use the complex analysis to write down this one, phi w. It's just a complex analysis is 2 pi I. And the contour integral CW, C, epsilon C. I mean, it's just a complex analysis, C minus W square. And then it's also as you can see, my energy is gone more than 2 pi I CW C epsilon C partial W phi of W and C minus W. Okay, so this is just if you do the contour integral, so if you do the 2 here, you just need to apply the derivative in epsilon, in d variable. I mean, CW is of course CW is W, and then CW is this one, and this is Z plane, okay. Z plane. Then so this is just a substitution Z equal to W. Okay. So if you use this one, one can just obtain the OPE of the stress. Oh my goodness, there's a typo here. So one can read off the under this delta phi. So now, so it's under the conformal transformation delta phi. So on the one hand, you have a component about Takahashi identity. On the other hand, from this variation, you get this. You can just apply this contour integral to here, and just compare with the between contour integral here and the contour integral here. And what you get is OPE with the stress energy tensor. So this is the most essential part of the conformal theory. C minus W square plus partial. Okay, so that's how you obtain. So you just substitute these two integrals into here, and compare with the conformal Takahashi identity. Then you get the OP with stress energy tensor of the primary, and plus I just consider only singular part. So yeah, this is the OPE of the primary field with stress energy tensor, and which appear many times during this lecture. So you have to be familiar with how to do the OP calculation. So one can apply the word Takahashi identity in correlation function. So this was done by very famous paper by 1984, developing So it's a very famous paper. It's a birth of 2D conformal theory. It's written coming from Landau Institute in Moscow. Landau Institute in Moscow in 1980. If you have chance, now it's coronavirus. You cannot go anywhere. But I visited many times Moscow. It's a very beautiful city, and then very beautiful city. And it's a very, Russia has a very nice culture for interaction between math and physics, and then this can be understood as one of the consequences of the interaction between math and physics. But yeah, and from conformal field, this is the birth of conformal field theory. And now, even now, there's Landau Institute, and you can visit there, and there is some. At the gate, there you can see the Landau's statue. And so anyway, it's written in Russian, Landau Institute. And it's a very nice place. It's very beautiful. I really like. Always, it's fun to visit Moscow. So let's move on to the. Where are we? Okay. So if you apply this stress OP with stress energy tensor, you can obtain the correlation function of the primary field. So you get acts on this correlation function. Okay, so this is the power conformal is so powerful that you can have if you have a correlation function of the primary field, one can have some differential equation once you take insert the stress energy tensor. Sometimes it's called BP's equation. Any questions so far? So this is appear in the homework some point in conformal theory. The conformal symmetry is so powerful that the 2-point function can be determined for primary field. So now we assume all 5 are primary. I2 Z2 delta H1 delta H2. So do you guys, yeah, so this is the 2-point function. Anyway, where H, so here, 2-point function is, when you consider 2-point function, the conformal weight, conformal dimension, H has to be equal, otherwise you get 0. Okay? So this is exercise in homework that appear to determine how this function. So I'm not going to explain how you determine. So you just use conformal symmetry to determine oh, is it a typo? There's a lot of typo. You should tell me if you find a typo. So conformal symmetry is powerful. 3-point function, the form of 3-point function is like this way. It's determined. And then so this D and Z are some constant, but I mean Zij is Zi minus Zj, of course. Up to constant, one can determine the 2-point function and 3-point function by using conformal symmetry. But now, so this C and D are really particular to the choice of primary field and the choice of the conformal field theory. And there's a lot of open problem to determine. The C, to determine C is not that easy. I mean, some rational conformal field theory and some CFD you can do that, but in general, it's hard to determine. This is called structure constant. This is structure constant. There are lots of open problem for given a conformal field theory to determine 3-point structure constant in 3-point function. A lot of open problem. So it's not that simple. Okay. Any questions so far? Yeah, I have a lot of Russian friends, physicists, also mathematicians. The reason why Russian physics is stronger, you know Landau-Lifshitz, right? Do you know Landau-Lifshitz? Have you ever read Landau-Lifshitz? Okay, seems like some of you guys don't know. There's so-called theoretical minimum. Landau-Lifshitz is a series of textbooks. And to be a physicist in Moscow, you have to read everything and then solve all the problems. And they also, like, the Landau is also made a really good work, did good work in statistical mechanics. Russians really has to study statistical mechanics in addition to the quantum mechanics, quantum field theory, and then conformal symmetry always appear in statistical mechanics and quantum physics. So that's one of the reasons why these 3 great physicists opened up new field. Okay. Any questions so far? So for multi-point, you need to use the so-called conformal blocks. So yeah, so you guys are still young. So once you have chance to go somewhere abroad, you should go. You should take a look at it after this coronavirus. It's a very nice experience to wander around the world. So the multi-point function, multi-point function is phi 1 to phi k, and what I mean is, so you need a so-called conformal block. Needs conformal block. So conformal block, I mean, you can have, for instance, if you have 4-point conformal block, and then so you have structure constant C 1, 2 alpha, C alpha 3, 4, the structure function of conformal, and then you can just usually put 0, 1, Q, and infinity. And this Q is called cross ratio. So by using conformal symmetry, one can fix 3 points at the position 0, 1, infinity. Infinity means, so in C is a Riemann, by Riemann map, C plus infinity is the same as 2 sphere. So one can put by using conformal symmetry, so 3 operator can be put at 0, 1, infinity, but there's another freedom for 4-point function, and everything depends on Q. Maybe here or not, sorry. And then you have to sum over alpha. So this is alpha, sum over alpha. This is the essential way to compute the 4-point function. So this is called conformal block. This conformal block. There are 2 ways to obtain conformal block. One is fusion of, that's called phi 1, phi 2, phi 3, and phi 4. Another is other way, phi 2, phi 3, phi 1, and phi 4. So there's another way to take another basis for conformal block. This is alpha and beta. And there are different bases for conformal block. And they're related by so-called fusion matrix, alpha, beta, 1, 2, 3, 4, and the sum over beta. So that's the relation between 2 bases of conformal blocks. So this is called fusion matrix, sometimes called 6J simple. But to obtain the explicit expression fusion matrix is very difficult. This one was, I mean, there's actually I'm personally working on to obtain this fusion matrix. So this one was first introduced by, as you know, Wigner and Raka around the 1940s. I think my spelling of Raka. So Wigner is famous mathematical physicist who made a comment on reasonable effectiveness of mathematics in physics. So the first introduced fusion matrix is into Wigner and Raka, and if given a conformal V3 or some conformal V3 to determine fusion matrix is very difficult. And this has very, very nice property. Okay, any questions so far? Okay, so shall we take a look at some example for 2-point, 3-point function for free field, and then let's finish. Then finish. So let's look at the Prescaler Theory, in which the stress energy tensor holomorphic part is this one. And I'm only focused on holomorphic part. Forget about the anti-holomorphic part. And we already know that the xc, xw correlation function is indeed alpha prime over 2 minus log c minus w. So I already forgot everything about the anti-holomorphic part. Focus on holomorphic part. So now, okay, there are lots of typos in my lecture. I'm sorry. Yeah. And so we already also know that JLC, for the translation symmetry, is something like a partial XC, and up to some constant somehow I just normalize I in this here. And so the question is, what is the correlation function of JZ and JW? So it's natural thing one can consider, which is just a partial XC, partial XW, and this is equal to minus alpha prime over 2 C minus W squared. Okay. So this one is just apply holomorphic derivative twice on here. Okay. Then you get the 1 over C squared, right? That's what you get. And do you see that? I'm doing very simple thing. So apply partial C and partial W in here, you get this one. Okay? And then, so let's look at the stress energy tensor OPE. So W, and now we're just doing this following OPE. So let's do the exercise. And here, you can take two ways, or either this one or this one. So both give the same answer, as you can easily see. And then so what you will get is that so let's first focus on, so it's the same thing. So if you apply this one and this one, you get the same object. So it's a twice of this one. And if you take the OP of this one, you get the alpha prime of over 2 log C minus W. So so what you get is minus alpha prime 2 and a partial C partial W log C minus W and a partial XC. That's what you get from OPE. Okay. And then so you will see the cancellation of between minus 2 over alpha prime minus alpha prime over 2, and apply twice the derivative, you get the C minus W square over 2. And I think I'll only focus on singular part, and I should use sin. And now, so this is equal to, if you do tail expansion here, with respect, so this depends on Z. So to the tail expansion, you get the XW, C minus W square plus partial square XW and C minus W. Okay, so this is, I just did a tail expansion here. Okay. Write down in terms of W. And here, if you take the first derivative, you get the, okay. And then they count. Okay, so therefore, if you compare with stress energy tensor with this one, with the stress OPE of a primary field, one can just conclude that this del x is primary field. As you can see, del x, if you replace phi by del x, what is the conformal dimension of the del x? What is h for del x? If you just compare with the result here, what is conformal dimension of del x? Just speak out. What's h for del x? 1. Yeah, so you can just compare this part and this part. If you just replace phi by del x, you exactly the formal there. Once you substitute h is equal to 1. Okay? So therefore, del x, so what we learn is del x is a primary of conformal dimension 1. H equal to 1. Okay, so that's what we have learned. Okay. Then, okay, maybe last step. Shall we derive OP of stress energy tensor? And then so finish. Okay, let's do the computation. So now we are going to look at TZ and TW for in Prescaler. So this is 1 over alpha square partial x partial xz partial x partial xw. Okay, so there are lots of ways to contract. So one is, let's do the following. One can take like this way. And then one can take another way, this one and this one. So it's the same 2 times this one. So therefore, this is 2 alpha square z minus w to the 4th over 1. And the minus sign here. Okay, maybe I think this one. Square. So you have a 2 copy of this one, okay? And another way to take OPE is that you just only take one of them, so one of them, and you just left it here. Then this will give you 4 alpha prime square alpha prime over 2 partial xz del xw and z minus w square. Okay. So the reason why I get 4 is that there's a 4 pair. 1, 2, and 3, and 4. Okay, that's 4 here. Okay. And minus alpha prime over 2, z minus w is just if you take OPE one of them, the two copy of x, you get the minus alpha prime over 2 over 1 of these. And this can be understood as already the Bell ranks. This can be rewritten everything in terms of stress energy tensor. At the end of the day, you get this equation. Okay, so this is this OP of stress energy tensor. As you can compare with this one and this one, if you can see that there's an extra term here, 1 over z to the 4th. So therefore, this means that the T is not primary field. So there is an extra factor here. So no longer, T is not primary. Okay, so that's today's lecture. Any question? Okay, so let's finish here, and then so homework is posted. So you have to do the contour integral of this one and so on. I mean, it's not that difficult homework today, this week. We just do the, from here you can get the Birasar algebra. So that's what we are going to do.